Hello all, I'm Siddharth Kaul and I welcome you to Edupedia World. In this video, we are going to take a look at basic modeling workflow in Simulink. What is modeling? Modeling is a process in which we describe a dynamic system with mathematical equation and then create a simplified representation of the system. The equations define the signs of the system and the model uses these equations to define its time varying behavior. There are three basic steps to modeling. One is defining the system, second is modeling the system, and third is integrating the system. Defining the system. In defining the system, we have four further steps, sub-steps, which we can say that is determining the modeling goals, identifying the system components, define system equation, and collect parameter data. We are going to look into each of them one by one. Let us start with determining the modeling goals. To help plan our model design, we need to understand the goals and requirements. So proper questions need to be asked. Like for example, what problem does the model will help us solve? What questions can it answer? And how accurately must it represent the system? Some possible modeling goals for us can be like we have to understand how the system components interact with each other, explore controller and fault tolerance strategies, decide between alternative designs, observe the response of system that we cannot solve analytically, determine how various inputs and changing model parameters affect the output. These are some of the key points we need to keep in mind while determining the modeling goals. Next, we have identifying the system components. When we understand our modeling requirements, we can begin to identify the components of the system. Identifying the components that correspond to structural parts of the system, creating a model that reflects the physical structure of a system. For example, motor control or a brake system is helpful when you have to build a part of the system in software and hardware. Then second is to identify functional parts that you can independently model and test. Third is describing the relationships between components. For example, what is the data transfer, what is the energy transfer, what is the force transfer, what is the rotational transfer, and so on. Fourth is to draw a picture showing the connection between the components, like it flows from top to bottom or bottom to top, from left to right or right to left. We have to include all the major parameters in our diagram. Creating a picture of the system can help us identify and model the parts that are essential to the behavior that we want to observe. Then defining the system equations. After identifying the components in a system, one can describe the system mathematically with equation. Deriving the equation using scientific principle or from the input-output response of a measured data can be done. You can use either of the ways. Many of the system equations falls into three major categories. That is, first is the continuous systems. For continuous system, differential equations describe the rate of change of variables with the equations defined for all the values of time. For example, as highlighted in yellow is a differential equation, is a second order differential equation that shows the velocity of a car. Then we have a discrete system. For discrete system, difference equations describe the rate of change of variables, but the equations are defined only at specific times. For example, highlighted in yellow is the control signal from a discrete proportional derivative controller. Third is the equation without derivatives are algebraic equation. For example, the total current in a parallel circuit with two components is given by algebraic equation of IT is equal to IA plus IB. These are the three types of equations that can be there in the system. Now we have the fourth part, that is collecting the parameter data. Collecting parameter data includes creating a list of equation variables and constant coefficient and determining the coefficient values from the published sources or by performing the experiments on the system. Using the measured data from a system, we define equation coefficients and parameters in our model. Using this data, we identify the parts that are measurable in a system. We measure the physical characteristics or use published property values. Manufacturer data sheets are a good source for hardware values. And we perform experiments to measure the system response to various inputs. We will later use this data to verify our model design with simulations. So after defining the system, we move into modeling the system. Modeling the system involves building individual model components that will implement the system equation. Also, modeling involves defining the interfaces for passing the data between these individual components. There are three major stages in models in the modeling a system. First one is top level structure. Model in Simulink is a graphical representation of a system using blocks and connection between the blocks. After we finish describing our system, it is components and equation we can begin to build our model. We use the system equation to build a graphical model of the system with Simulink editor. If we place all of the models in a one level of a diagram, our diagram become difficult to understand. That's why we have a top level structure. So one way to organize our model is to use subsystems. Examples of block that we can use to create subsystems are like include subsystem, atomic systems, and model. Third, we need to identify input and output connection. For example, signal lines between these subsystems. Input and output values changes dynamically during a simulation. Next, we have model component. Some questions to ask before we begin to model a component is like, what are the constants for each component and values that do not change unless you change them? What are the variables for each component and values that we need to change over the time? And how many state variables does a component have? After we create the top level structure for our model, we can begin to model each individual components. We use the system equations to create a Simulink block. We add the Simulink blocks in the Simulink editor. Blocks represent coefficients and variables from the equation. We connect blocks to each other, and lines connecting these blocks represents the data transfer. We build the model for each component separately. The most effective way to build a model of a system is to consider each of its component independently. We start by building simple models during approximation of the system. We identify assumptions that can affect the accuracy of our models and iteratively add details until the level of complexity satisfies the accuracy and the modeling requirements. After we build a model component, we can simulate to validate its design. So third component is the simulation of the components. We predict the expected output of the integrated model components. We add blocks to approximate actual input and control values. We add sync blocks to record and visualize data, where we add scopes and other visual things to analyze the data. We validate the model design by comparing the simulation output to our expected output. And if the result does not match our prediction, we change our model to improve the accuracy of our prediction. This change may include at model structure level or parameter level, or even at a constants level. Now, integrating the model. There are three steps to integrating the model. We have to connect each of the model components, then we have to simulate these connected components, and we have to model the external interface. Connected model components. After we build and validate each and every model component, we can connect them into a complete set of model. Then we simulate this model and analyze the results. There are some guidelines that we need to there are some guidelines for connecting model components. We integrate model components by first connecting two of them. For example, connect a plant to a controller, and after validating the pair by simulation, we continue adding components to it. We think about how each of the component can affect the other parts of the model. Like for example, adding a plant or adding a delay to a plant controller may will delay the control action of the plant, and so on. Next is simulating the connected components. Validating our model determines if it accurately represents what we are looking for. It should accurately represent the physical characteristics of the modeled dynamic system. For validating subsystem, we predict the expected simulation results and outputs of the subsystem. We add realistic input using source blocks. We add sync blocks to record and visualize results. We simulate the subsystem and compare the simulated results with our expected results. If this all satisfied, we can say yes, our connected components block simulated properly. Third part is model the external interface. A block is ready, but how will it interact with the external world? So for that, we need to have signals in and out of our model. So these adding the blocks for these external signals from coming inside the model and going outside the model is what is called modeling the external interface. This concludes our video on basics of modeling workflow. In the next video, we are going to look into basics of simulation workflow. Here we will discuss about the simulation. So until then, please subscribe and thanks for watching.